So in this video, we're going to talk about how to solve a second-order reducible differential equation. So in this equation, we can see that the independent variable is missing. So if y is a function of x, then x would be our independent variable, and y would be our dependent variable. And we notice that x is missing explicitly from this equation. But we also notice that y is also missing explicitly from this equation, which indicates that we can solve this equation one of two ways. For the purposes of this video, I'll show you how to solve it both ways. So the first way to solve it would be to let an arbitrary constant, say v, equal to y prime. And then alternatively, dv dx, so the derivative of v, equals y double prime, because we've just differentiated v with respect to x, and so we're going to have to differentiate y prime with respect to x again, and that gives you y double prime. So we substitute everything back into the original equation. Y prime, v prime, and so we have v prime equals v prime plus v equals 0. And so I'm going to rewrite this as dv dx equals negative v. And then we have from here 1 over v dv equals negative dx. From this point, we take the integral on both sides, and we get ln v equals negative x plus c. So to isolate for v, we take the exponential of both sides, and we get e to the negative x plus c. We know that e to the negative x plus c equals e to the negative x times e to the c. And e to the c is just some arbitrary function, arbitrary constant that we can call k. So we have v equals k e negative x. And then from here, we're actually not done because we've defined v as y prime. So let's substitute y prime back in. Because v is I would call a helper variable, where it doesn't appear in the question, therefore it cannot appear in the solution, but it helps us solve the equation. So we have y prime equals k e negative x. So when we integrate both sides, we get y equals negative k e negative x plus c 1, not to be confused with the original c. And so we have two arbitrary constants, which makes sense because we have a second order differential equation, and so we produce two constants that would require two boundary conditions to solve.